Hi all. In this video, we see a paper titled Overtaking Maneuvers in Highway Driving Using Deep Reinforcement Learning from IIT Hyderabad. And in this paper, they developed two main things. One is a curriculum-based learning approach to train an agent based on deep deterministic policy gradient of a reinforcement learning technique for learning and overtaking maneuvers in a highway driving. So what they says is this present scenario, self-autonomous driving has become a significant progress due to low-cost sensors and availability of amount of large driving data, and also we have many upgradations of the learning uh, algorithms like deep learning packages and reinforcement learning algorithms based on deep learning. So prior to that, the author also discussed some of the literature review. One among this, as we all know, that Alvin, which was artificial neural network based end-to-end learning, where they use image data to compute the steering angle directly instead of using a conventional mediator perception approach. So later they also developed some recurrent neural networks for making an end-to-end learning or imitation learning method, and later they also adapted some kind of direct perceptions where they try to learn some affordances using the sensory data to make a behavior uh, hierarchy to make a behavior driving decisions. So in this paper they use a kind of a reinforcement learning, and prior to that there are some attempt has been done deep reinforcement learning has been utilized for autonomous driving in these papers, and also some attempts are also done using inverse reinforcement learning where they try to learn the objective like cost map for autonomous driving directly from the sensory data. So this paper attempts like a reinforcement learning based on a deep deterministic policy gradient to make a continuous actions like steering, pedaling, and braking, and they make some kind of curriculum based techniques where they learn a simple scenario first, then they introduce into a complex maneuver like an overtaking. So this the first works they claim that to be using curriculum learning based deterministic policy gradient reinforcement learning. So deterministic policy gradient is similar to like of a deep Q networks where they recently used for Atari games, and they have a four principal techniques being embedded in this one. One is a replay buffer where they collect many samples data. The agents are allowed to play many number of episodes, and those timestamped episodes are collected and they are randomly sampled, making a mini batch to have some to train those neural networks, namely the actor and critic networks. And here as well as they don't use the directly the updated parameters, they make some kind of an weighted average so that the uh, already computed parameters are being stored temporarily in networks called target networks and target actor and target critic networks, and those parameters are updated and those parameter weighted averages are updated. It always this gives some kind of an improving stability instead of using directly these parameters. So this is kind of a weighted average where it will be between a 0 to 1. And they also said that the input data can have a different scale, so some kind of a normalizations can help minimize the variance and making the data center around the unit mean and unit variance. And the last one would be like the deep deterministic learning is an off policy algorithm where they have some kind of the learning strategy is based on these equations 2 and 3, where equation 2 is being utilized to update the critic network and equation 3 is utilized to update the actor network. And this ri is the reward function of the right time step, it's a target network parameter. So and this is the output of the action network, and this is the target q values where this is the objective to be minimized one. And as mentioned that gamma is a discount factor, and which is added with the cumulative discount factor. So the curriculum learning is one of the important contributions given in this paper. What this says is they first try to, like a human way of learning the process. They try to learn a simpler task first. Then they introduce into the complex task, which the prior simplest learning task will guide you to learn a complex task much in a quicker way. So this is the overall algorithm of the deterministic policy gradient. Like we have randomly initialized the actor and critic network that has been given in the below figure, which will be showing in a few minutes. And this is a target network, and the parameters are saved in a separate variables, and have this many number of episodes and this many number of timestamps, and the actions, and for every steps an action is given, and it will be updated state, and the update reward is obtained, and those are kept in a stored in a space, and those are randomly sampled, and have this as a mini batch, and those are learned and trained to update those parameters of the actor network and the critic networks. So this agent is being embedded trained. This agent is based on the talks environment, especially a gym talks. It's a reinforcement learning environment, and the agent is called SCR server 1, and they train in a GTX GPU NVIDIA force. And the figure 1 and figure 2 gives you the actor and critic network. This is the fixed 65 dimensional input vector for the actor network, and which gives you three values: steer, break, and value. It's between 0 to 1. This also steering is -1 to +1. And also a critic network, that the actor network's input and the present state vector is given, and it computes the critic values, like maybe in the q values for the acceleration, steer, and the brake values. So these are been given here. These are the actions, three-dimensional actions values. These are continuous actions. And for the first, I said, like curriculum learning approach. First, this lane keeping behavior is learned using an objective function called objective function based on this equation 4. What this is, this is traveling along the track. This, when it is deviating out of the track, it is been penalized, and also this is penalized if the value of time is kept increased. So it's beautifully designed uh, objective functions. Along with that, these are the things explained here, that this gives you a positive reward and negative when it moves laterally, which is being given by the sine theta. And also this the third parameters, like if we are having a higher velocity, this will be reduced. If we are having lower velocity, this will be increased. So it will be try to minimize this value as much as possible. And the second hierarchical approach is overtaking. Along with that first equation, this augmented with the second term called this is like race positions. If we are in the last position, we will be more penalized, and we are trying here this terms will become 0 and the reward will be reduced. And if you are coming to the first position, then we will be in a higher value, and this higher value gives more overtaking, so it will try to maximize the reward. So the race positions will try to keep to number 1 rather than to the last value. And in addition to that, if there is a collisions, then the reward will be more penalized, and if you are going drifting, that will be more penalized, and there is no like kind of progressions, and that also will be penalized. And if we are having a successful, that n value changes, this race position changes, this will give an additional benefit, and the race value kept decreasing, this will be penalized by 2000 values. So this has been trained. These are the training parameters, and the noise is first introduced to have more explorations. And once that episodes are kept increasing, then the noise value are kept decreasing by a factor of 0.0 at every time step. So we are using a 2000 episodes for training the overtake and 1000 episodes for learning the initial lane keeping behavior. So the observation is the agent could train on a single track with 4 neighbors, and if they could able train, and it could able to generalize to car of 10 neighbors as 10 neighbors as well. And this parameter plays a big role in equation 5. and it also tries to if we are not using this one, the agent couldn't able to learn the overtaking maneuvers, and also that in a straight line it couldn't able to identify how to overtake and how to make. So how it doesn't go for a follow up mode, just it tries to overtake the car as much as possible. So that colliding is happening at the various scenarios. So again said, this is for overtaking, and this for something not having that overtake is penalized. So another important factor that we could identify here is first the lane caping is done for a certain episode, then the overtaking is being done. If there is not lane caping or pre-training is not being done, the car was not able to learn overtaking without this additional training and efficiently. So this is the first A is a relevant observation. Third one is with curriculum learning. So this curriculum learning plays an important role. For example, if the first we could able to learn through the lane keeping, then the overtaking. So this gives you a very added advantage, and the agent could learn properly. If the curriculum learning is not there, then how does this behavior is shown in the figure 6. What this is it collides into the car and it moves away from the track, and it is very hostile and unsafe behavior which cannot be countered in overtake maneuvers. And what would be the result if we are not adding the lane keeping terms here? If the lane keeping terms, that first term in the equation for the overtaking behavior is not added, this lane keeping, that equation 5, this lane keeping lane keeping terms are not added into that, then what would happen is these are the results they identified, that overtapping component alone being utilized. Then what would happen is the percentage episode where the agent did overtake go ahead of reduced drastically. This overtaking behavior is that efficiency is reduced drastically, and also there is a high ended up when colliding with the neighboring cars. So this paper is a nicely written paper from Indian authors, and they have given a very brief and crispy and clear understanding of how a deep deterministic policy gradient can be trained for overtaking maneuvering in a simulated autonomous drivings. So, but although they have kept in a simulation driving, this is giving a nice potential to try for a future in a realistic scenario based on a visionary based data, because these have used only the sensory data, where the sensory data are being utilized is been given in this list. So these are the some sensory data like a 65 dimensional vector. These are based on these informations in the talk simulator has been given as an input to this actor network and the critic network. But future this information like sensory information can be replaced by vision information from the directly giving the image pixels to train the actor and critic networks. And moreover, this has used uh, only a one timestamp data, but we can later maybe a future work would be to utilize reinforcement learning, like utilizing multiple historical timestamp data, so that the learning can be happening more stable way. So there should be another research future, maybe leveraging the power of recurrent neural networks in tackling problems associated with the partially applied data. And as mentioned earlier, there would be a visionary sensory input instead of the sensor data from the simulations, right? So the future work, as author said, there will be a strong vision-based module moving into a direct perception approach. Thank you.